To wrap up new topics today, let's talk about a totally different approach called uniform partitioning that will also serve as a soft introduction to what we'll be doing later, something known as hashing. So in this approach, let's say we want to, again, try and find the item that is closest to the space horse, or the items that are inside a green rectangle. Well, in this approach, we don't consider the data at all when we're trying to partition our space. Instead, we just put everything into uniform rectangular buckets, also called bins. So for example, if we have 16 such buckets or bins, it would look like this. So the space horse is in bucket 1. So question for you, just to get a sense of how this might help us, which buckets do we need to iterate over to find all points in this green range? Okay, so it's as easy as it looks. You only got to look at buckets 5, 6, 9, and 10. So that means that if, again, there's a whole lot of points in bucket 13 right here, you don't have to look at them. And so the algorithm here is still theta n, but it's faster than iterating over all of the points. So in this case, maybe we do roughly n over 4 of the work, something like that, assuming the data is evenly distributed. Still, n over 4 is better than n. And so in practice, it turns out that people often use this approach instead of a quad tree or a KD tree. So if we compare these two different philosophies of how to partition space, in this uniform partitioning approach, which is just so simple I didn't spend any time really on it, we have a grid of rectangles. But on the right, this hierarchical partitioning approach, in that case, we have our data actually own the subspaces. So again, I'm showing here the quad tree subdivision of the space, but KD trees do the same thing. They still subdivide their data into subspaces. And we had the situation that spaces are more finely divided into subspaces where there are more points. But over here, we don't care in this uniform subspace approach. So I'll note that uniform partitioning is a lot easier to implement than a quad tree or a KD tree. And for many applications, it's actually good enough, including the situation where you're going to use it in this class. That said, I still want you guys to get some practice with this, because in really high performance applications, this uniform partitioning approach might not work as well as a quad tree or a KD tree or an oct tree. And actually we'll see in the very next lecture that there is a very clever 1D version of this idea that's called a hash table. And so this idea of just basically bucketing our data ends up being more general than what we see here. Just a fun aside. Okay. So I'm just throwing that out at you. If someday, I don't know, you're building some application and you don't have in your language a quad tree or a KD tree, it's okay to just do this little hack, this uniform partitioning hack. But in our class, since it's about data structures and I want you to understand these deep and beautiful ideas, we're going to be focusing on quad trees and especially KD trees.